Welcome everyone to today's PROCLIAS and ISIMIP webinar on climate impact attribution. And it's my pleasure to introduce today Friedrike Otto. Freddy is a senior lecturer at the Graham Institute for Climate Change and the Environment at the Imperial College in London. And her research is focusing on trying to answer the question whether and to which extent anthropogenic climate change is influencing extreme weather events. In this context, Freddy did, for example, co-found and is still leading the World Weather Attribution Project that is dedicated to assess the influence on ongoing climate change on recent extreme climate and weather events. Given this activity and her impressive track record on publications in the field, I think it's safe to say that Freddy is one of the world leading experts in the field of climate attribution science. And I'm very much looking forward to her lecture today.
Thanks very much. I will share my screen. You can see that, hopefully. Very good.
Yes.
Yeah. So I've seen some in the audience have actually worked in this area before. So I'm afraid Sven or Sabine, you might be a bit bored at the beginning because I think most of the people attending don't know what how extreme event attribution exactly works. So that's where I will start with, and then talk about some more about the implications. But I would like to start in the same way I always start, which is with some version of this or variant of this figure. We are long in the era of loss and damage. And even though in the public discussion and still in political discussions, climate change is always talked about in future terms, or almost always talked about in future terms and as a future threat, and we are interested in assessing future risks. Of course, it has been happening for a very long time, and the impacts of climate change have been felt for decades. So, which is also why we are doing attribution, to find out what of the things that are happening are actually because of human-induced climate change. But it's also really important to point out, and this is why I have this video of my friend Adam here. Climate change, for most of the events that we are concerned with, and that is how climate change manifests on society, changing risks and intensities of extreme weather events, they get worse the more CO2 and other greenhouse gases we emit. But it's not that 1.5 is a particularly dramatic point in time. It's a political goal. And so if we reach 1.4 degrees, that'd be better than 1.5 degrees, but 1.6 degrees would also be a lot better than 2 degrees or warmer. So it's not for extreme events. Most of these changes that we see and that we observe are linear with global mean temperature, which means that lots of these changes have already happened and are already happening, and they get worse the warmer it gets. But there is not a particular point where suddenly the nature of these types of extremes is changing. But how do we know this? And how do we know how climate change affects extreme weather events? The idea behind this is actually very straightforward. And you can see here on this slide 2 versions of the same thing. Just one is from the FAQs in last year's IPCC report, and one is from an earlier paper where we have where you see probability distributions. Because climate change affects extreme weather events in 2 ways. One, just the warming effect alone, because we have more greenhouse gases in the atmosphere as a whole gets warmer. That means overall there's an increase in the likelihood of heat waves and decrease in the likelihood of cold waves. Warmer atmosphere can hold more water vapor that needs to get out of the atmosphere. So there's also overall an increase in heavy rainfall. But of course, because we have changed the composition of the atmosphere and the temperature distribution, that means also the atmospheric circulation has changed. And this can be in the same direction. So we can have, because of the warming, more heavy rainfall, but we also get more low pressure systems conducive to rain. So overall, you have a stronger effect locally in a particular region and a particular season for increases in heavy rainfall. But those effects can also work in opposite directions. So you have fewer low pressure systems or conducive to rainfall. So you don't actually see a change in the likelihood and intensity of heavy rainfall, or you see even a decrease. And because this second effect is very different depending on the region, depending on the season, and depending on the type of extreme event, we can't say, without having done actually studies on these particular types of events in the particular season and region, how exactly climate change is affecting weather today. But we can do these studies. And this is what you see here on this slide. What we do is we find out what is possible weather in the world we live in today. So let's say heat wave in, because I'm just seeing Lukas, heat wave in Zurich. So we want to know what's the role of climate change in the heat wave in 2018 in Zurich. And to find out, we need to know what are possible heat waves in the world we live in today in Zurich with anthropogenic climate change, with the amount of greenhouse gases in the atmosphere we have now, with 1.2 degrees of global warming that we have now. And we can use observations and statistical modeling and climate models to find out what are possible heat waves in, or possible temperatures in the summer in Zurich, in the world we live in today. And then you get something that looks like the red curve on these two graphs that gives you, this is the likelihood of high temperatures or temperatures in the world we live in today. And then we can say, okay, we know that mortality really increases above a certain threshold, or this is a threshold that we have measured. So we use that to define our extreme event. And then we get a likelihood of this event to occur in the world we live in today. So this is what you see here in the shaded curve. And then, because we know very well that it was 1.2 degrees colder at the beginning of the Industrial Revolution, and also how many greenhouse gases have since been put into the atmosphere, so we can simulate the world that might have been without climate change, and then get possible weather in the world, possible temperatures, summer temperatures in Zurich in the world that might have been without climate change. And in this completely exaggerated schematic here, you then get the blue curve that gives you the possible temperatures in that world. And then you can look again at your threshold that you've used to define your extreme event. And you find that in this case, maybe the likelihood of such a heat wave to occur is not 1 in 10, as it was in your first type of experiment, but it might be 1 in 100. And because the only difference between these two worlds is human-induced climate change, you can then attribute the change in likelihood or the change in intensity, depending on what you're looking at, to human-induced climate change. So that's the idea behind event attribution, which is not really actually intellectually very complicated. Doing these in individual cases then often ends up to be quite complicated. There are some typical results of these kind of studies. So this is one that we did last year together with world weather attribution on the extreme heat in Canada and northwest of the US, where close to 50 degrees Celsius have been measured in Canada. And in that case, we found that the likelihood of this event has increased so much because of human-induced climate change. It would have been basically impossible to occur. So the likelihood of ever occurring without climate change is so small that you can say it's basically, yeah, an event that would not have occurred. And it's still a rare event in today's world, but climate change is a real game changer in this case. But that's definitely not the case for all extreme events that are happening and that have impact. So this is another example of a study we did last year on a drought in southern Madagascar that led to huge food insecurity and famine. And there we found that actually, yes, it was an extreme drought. So there were 2 years of very little rainfall in the rainy seasons, but it was not outside of what you would expect from natural variability. And it was not a type of event where climate change actually changed the likelihood or intensity of such an event to occur. But the reasons for the dramatic impacts were in the very high vulnerability, also exacerbated because of COVID, so that NGOs and other aid measures could not get where they needed to be. And so the impact of the drought on the population were dramatic, but it was not because of climate change, but because of other factors that vulnerability and also dependency on naturally quite unpredictable or unreliable rainfall. So these were just 2 examples, and this is one example a lot closer to home, which is for an extreme rainfall event associated with winter storms in the UK, which we just had. Again, this is a few years back, but I would be very surprised if it would look very different this year. And this is how, with real data, these kind of curves that I've showed schematically earlier look like for heavy rainfall associated with winter storms in the UK. And you see here the same thing that I showed earlier with the 2 distributions, but just plotted as a return time curve. And so if you're a hydrologist, you know much better what this is. If you're not, you have on the y-axis, you have your measure of the extreme event. So in this case, it's daily precipitation in millimeters per day. And on the x-axis, you have the return time of the event. So if you look at the event that has occurred here, with this shown as the dashed line, you can see that it's in today's climate, which again is the red curve. So all of these are simulations of possible rainfall event in the winter in the world we live in today. You can see that it's about a 1 in 20 year event. And when you look at the same thing in simulations of the world that might have been, you can see that there is a decrease, an increase in the likelihood of this event to occur by about 40% because of human-induced climate change. Or you could look at the intensity change. So an event that has a 1 in 20 year return time today is about 15% more intense than it would have been without climate change. So that's these likelihood and intensity are just 2 different sides of the same curve. You can always look at either or both in these event attribution studies. So this is how real results look like. But the really complicated part of event attribution is not the attribution. The really complicated part of an event attribution study, of every event attribution study, is always what is actually the extreme event. How do we define the event in order to say something about the real world? Because we do event attribution studies because we want to say something about the real world, about the extreme events that people have just experienced or are just experiencing that have led to losses and damages, losses of livelihoods, lives, economic losses. So in order to do that, we need to link these losses and impacts in the real world to something that we can usefully measure with meteorological data, where we have meteorological data for, and that we can in some way reliably simulate with a climate model. And this sounds relatively trivial, maybe, but it's actually really difficult, because quite often you have reports on, okay, there's flooding in Kenya, which in this example. So can you do an attribution study? And there you might have pictures of floods and also some reports about the impacts. And if you're really lucky, you have some station data with rainfall records, but it might not be that the station has been actually in the place where it has flooded. So you need to first find out what has actually happened in terms of rainfall. And this is just really to illustrate the issue. You see here two different types of observations or pseudo observations of rainfall on the same day, on the 10th of November in Kenya. And you can see on the left-hand side, there's a big heavy rainfall event in pretty much the center of Kenya with up to 50 millimeters of rainfall in a single day. But in the other product, there's nothing like that. And so without any experience, without any additional ground-based station measurements, it's almost impossible to identify what has actually happened. So this is a relatively extreme example, but some lighter version of this problem always happens when you try and find out what has actually happened. How can we define an extreme event? And of course, this is just if you know which variable to look at, which is if you know that it's pluvial flooding, then that rainfall is the right variable to look at, is relatively straightforward. But for example, when we talk about heat wave, and this is an ancient example, but it still shows the problem quite nicely. So you can define a heat wave based on temperature alone. And you can define it on a relatively large geographical scale, or you can define it on a very small geographical scale. And you can say, okay, we're interested, it was actually not just a heat wave, it was a very hot summer. So we look at the heat wave just at hot summers. And this is what the example you can see on the left-hand side, again in red, simulations of possible hot summers in the world that is, and in blue in the world that might have been. And in this example, you see that because of climate change, the likelihood of this very hot summers, or summers as hot as the one observed in 2012 in Serbia, has increased by a factor of 100. And you say, okay, but we care about heat waves because they affect the human body. And so heat stress is actually the variable that is most relevant to the impacts. You can say, okay, we can define a heat wave based on heat stress. So in this case, wet bulb globe temperature. So a combination of humidity and temperature. And in this case, you still find there is an increase because of human-induced climate change, but the numbers are completely different. And this is not the one is right and the other is wrong. It's just a different way of defining the event, and therefore it's speaking about a different aspect of the impacts that these extreme events have. And so before or when you do an event attribution study, first of all, you need to find out what happened, but then you also need to find out, okay, what of the things that happen are we actually, what do we care about? Where do we have data for? And then you need to come up with an event definition. And then you have done an event definition, you can start with the actual attribution study, where the next step then is, okay, we have now some data, we have an event definition, we have a rough idea what happens. Do we actually have climate models that are able to simulate this type of event that we are interested in a reliable way? And so the next step that is to look to do some model evaluation of the climate models that you have available. And when we do a study with world weather attribution, we always try to use as many climate models as we can get our hands on, which is depending on the type of event, that can be 70 or that can be 4. And then you do model evaluation. And I think that's a very open-ended question of how you do that, which is not the topic of this lecture, but we can talk about this later if you have questions about that. But then, having done model evaluation, you usually end up with some climate models that you have decided are fit enough for purpose and that you can use for an attribution study. And then you do, or we do, the same thing that we have, that I've just shown earlier, with the models, statistical modeling based on the observations and with the different climate models. And in this example here, that we have station data and 2 high-resolution models. And in an ideal world, you would have a result that looks something like the one that I show here. So you have different lines of evidence because you use different models and slightly different methods. And with each of these methods, you get the change, in this case, in likelihood. And what you see here in blue is the change in likelihood based on observations. It's just 2 different sets of observational data. And there you can see, so the dashed line here is the one that would be no change. And so in the observations, you have about a 2.5. So the black bar is your best estimate statistically, and the blue bar around that is the sampling uncertainty, gives you about a 2.5 times increase in the likelihood of this event to occur, which in this case was heavy rainfall after a tropical depression in Texas. And then here we have 2 different types of high resolution climate models that in this case give relatively similar results. So you can just synthesize these results by basically averaging over them and say we have the likelihood of this event has increased by a factor between 1.6 and 3 because of human-induced climate change. So that would then be your result of the attribution study. And this is an example of where everything goes very nicely, and you have results that are all within very similar orders of magnitude, and you have models that you can use, and that sort of you have also some physical understanding of why these increases are expected. This is not always the case. So this is just really to illustrate how different these types of results can look like. So what you see on the left-hand side is the result of the Madagascar study, of the drought in Madagascar that I showed earlier, where we use lots of different models. And insofar, it's still a relatively straightforward result, because in none of the simulations of the models and also the observations was there a significant change in the likelihood of the event to occur. But you can also see that the models show quite a very large change in likelihood, or a very, very large margin, which in many cases is just because we didn't have large ensembles. So the sampling uncertainty is just huge. But it also means that there could also be things going on that we just don't know, and that we, by the statistical approach, don't really see. We have no reason to think that one model is better than the other, but it's not a very satisfying result to have so huge uncertainty margins that basically allow you, well, it could be no change, but it could also be 1,000 times increase in the likelihood. So this is where then the synthesizing becomes much more of an expert judgment exercise rather than just a statistical weighing exercise. And this similarly is the example that you can see here on the bottom right corner for the heat wave in Germany. There, the sign is very clear. We know that every heat wave that happens these days has become more likely, more intense because of climate change, and we also see that in the data. But you also see that here in the observations, we have, as the best estimate, about a 500 times increase in the likelihood of the event to occur. But all the models show significantly lower change in likelihood. So this is something where you think there's probably something that the models, there's something systematically wrong with the models, probably. Or in this, if this was an isolated case, you could also say, well, there's something else that has changed, some local drivers that have changed the likelihood of heat waves. But because we see the same thing everywhere in Europe, that's and also in other parts of the world. So in Australia, we have seen the same thing. In the US, we see the opposite, that the observations are very systematically lower in change than the models. So which also makes it very difficult to quantify the result of your attribution study. So in this case, for the heat waves, we would say that, well, because of climate change, this event has been made at least 10 times more likely, but this is the lower bound of what we think is happening, but we can't quantify it better because the upper bound is completely ill-defined, and the best estimate is also not telling us very much. So to summarize, when we do an attribution study, there are a priori 4 possible outcomes. The event could have been made more likely or less likely. It could be that there is no change, or it could be that with our current understanding and tools, we can't say. So it can be, it has happened in quite a number of cases that we actually don't have any model that passes our evaluation tests, and so we can't really do an attribution study. And of course, there are types of events where, like tornadoes, where we don't even try because we actually know that we will not find climate models that we can use to do this study. But of course, and I've said earlier, you have to do attribution studies because we have these 2 effects, the warming effect and the dynamic effect, and you don't know how the latter a priori. So you have to do an attribution study on a certain type in a certain region. But of course, now we have done lots of these studies. And so there is actually a lot of information without doing an individual attribution study that you have and that we can use to inform our communication and also our expectations on how climate change is affecting individual weather events. So this is really this last IPCC report that has been the physical science basis, the one that has been published in August, not this week, has for the first time really systematically also assessed results on papers doing attribution studies. And this figure 3 from the SPM is sort of the result of what we can say on a very global, very synthesized scale. And unsurprisingly, this one is for heat waves. So each of the hexagon is a region in the world. The red hexagons show an observed increase in extreme heat. And the dots underneath the acronym of the region's name show the confidence in the attribution. So whether this is because of human-induced climate change and how confident we are in that knowledge. And you see that from apart from very few regions, we have a strong evidence base that heat waves are increasing and that it's because of human-induced climate change. This looks quite different when you look at the panel B of this figure, which is for heavy rainfall events. There it's in green, where we do see an increase in observed heavy rainfall. And you can see there are a lot fewer green hexagons than there were red hexagons before. But you can also see there's just one region in the world, and this is Northern Europe, where we have actually high confidence in that what we have observed is because of human-induced climate change. That's not because we have in general very low confidence that heavy rainfall is increasing because of climate change in the rest of the world, but it's because what the IPCC does is looking at published academic papers on the change in heavy rainfall and then the attribution and heavy rainfall. And there are just not that many in most parts of the world. So the evidence base is just a lot smaller than it is for heat waves. And in particular, in all these places where the hexagons are gray, we don't actually have any papers or any academic studies that either look at observations in changes in heavy rainfall or do an attribution study. So this figure shows very clearly that our understanding is very skewed towards the global north in terms of how climate change affects extreme weather events, and that there are huge gaps in large parts of the global south. Of course, this is the sort of IPCC synthesis average. So we do know a bit more than has been shown here, because IPCC averages over these large regions. And also there's a cutoff date for the literature and new studies come in. So this is, if you're interested in finding out, has an attribution study been done on a certain event, this is a good resource to go to. So Carbon Brief, which is a UK-based climate and energy news agency, they have a website that they update once a year where they collect all attribution studies to extreme weather events, and they have this map, which is also interactive, so you can click on these things and look at the underlying papers and show what we know in terms of published literature on extreme weather events in the world. But of course, this is absolutely not representative of what is happening in terms of extreme weather events around the world. So in this map, I have tried to illustrate the discrepancy between things that are happening and that are having bad impacts and what we know about the role of climate change in these events. So what you can see here in red are deaths associated with extreme weather events in different countries in the world. So the circle is always on the capital of the country. The larger the circle, the more death associated with extreme weather events as a measure for impactful extreme events. And overlaying these red circles in black is extreme death associated with extreme weather events for which we do know, based on the published literature, the role of climate change. And you can see when you look at Europe, or here, for example, this big circle over Moscow, that's basically two big heat waves that had a huge death toll in Russia, but for which we do have attribution studies, so which is why there's a big black circle. So we do know the role of climate change in these events. But in most of the countries where you see only red circles, it's a mixture of different types of events and where there are basically no attribution studies. And so while we do have the tools to do these kind of studies now and to actually causally link what we observe in the world with climate change or not, it's only done in a very small subset of the events that are actually happening. And of course, I have, in order to do this map that I've just shown, which uses death associated with extreme weather events reported in EMDAT, which is a global database of disasters and their impacts, and amongst other disasters, climate and weather related disasters. But when you look at this database and you look at heat waves, you can see, which is what you see on the big map here, that most of sub-Saharan Africa is basically blank. So there are no heat waves in Africa, which of course is not the case. When you look at observational data of temperatures, you do see a huge increase in heat extremes also in sub-Saharan Africa. But these are not, there's no heat wave warnings, so there's no measures by the Met services on heat waves. And so the impacts and effects are not recorded and don't end up in any databases, and so are also don't end up as something that is actually being studied. So it's not just that. So the problem with what is actually happening is really starting already by what are we actually thinking about when we or what extreme events do we actually notice, which for heat waves is of course a big problem because people don't tend to drop dead in the streets, but quietly die in their poorly insulated houses. So it's not something that is immediately obvious, which is why the recording is more difficult. And so yeah, I would just like to stop with one last slide here, which is, of course, when talking about extreme event attribution, there comes always the question of, can you sue someone for the damages? And because the idea of doing event attribution the way we do it actually comes from epidemiology and from causally linking smoking to cancer and asbestos exposure to mesothelioma. So these kind of epidemiological causal relationships, which of course then have subsequently been used in courts to sue those who sell tobacco or asbestos, and so it could be used against those who dig out fossil fuels. And in theory, that could well be the case. In practice, the ongoing cases, and there are quite a few at the moment, there are about 80 damage cases where actually countries or companies are sued because, and they are interesting in terms of the scientific evidence that is used, because it's way behind what we actually can say scientifically. So it's not linked to any scientific evidence, but it's usually just linked to observed damages, which are of course not just because of the hazard, but because of vulnerability and exposure and response mechanisms and the hazard. So by linking what we bring to courts and what we can say scientifically a bit better, that could be something. So there could be quite successful damage cases also in the courts and not just in academic journals. And yeah, I'll stop here so that we have time for questions.